Now we are going to take up ideal gas equation. It correlates all the four parameters of the gas. It is combination of Boyle's law, Charles' law as well as Avogadro's law. And the ideal gas equation is PV is equal to nRT. N is number of moles of the gas. How to find out number of moles? It will be mass of gas divided by molar mass of the gas. So our equation becomes PV is equal to small m, which is mass of the gas, divided by capital M, which is molar mass of the gas, into R into T. Now Pm is equal to mass per unit volume into RT. We have interchanged V and M, so we get Pm is equal to mass per unit volume into RT. Mass per unit volume is density, so we get Pm is equal to dRT, or density is equal to Pm over RT. D is density of the gas. So in these equations, N represents number of moles of the gas, small m represents mass of the gas, capital M represents molar mass of the gas or molecular weight of the gas, and R represents molar gas constant. For 1 mole of the gas, N will be equal to 1. So PV will be equal to RT, or P1 V1 over T1 is equal to P2 V2 over T2, which is equal to constant equal to R. Or simply we can write P1 V1 over T1 is equal to P2 V2 over T2. This equation will be used in numerical problems, where P1 V1 T1 are initial pressure, volume and temperature, and P2 V2 and T2 are final pressure, volume and temperature. So the above equation is called ideal gas equation. The unit of R is the unit of work or energy per degree per mole, obtained as R is equal to PV over NT. P is pressure, V is volume, N is number of moles, T is temperature. Pressure is force per unit area. So we have replaced pressure by force per unit area into volume divided by moles into temperature. Now area and volume. Area is A square, volume is A cube. So it will come out to be force into length divided by moles into temperature. So R will be force into length will be work or energy divided by mole into temperature. Numerical values of R in different units are R is equal to 0.0821 liter atmosphere per Kelvin per mole. R is also equal to 0.083 liter bar per Kelvin per mole. R is equal to 2 calories per degree per mole, and R is equal to 8.314 joules per Kelvin per mole. So the value of R is different in different units. Next we are taking Dalton's law of partial pressure. According to this law, when two or more than two chemically inert gases, here chemically inert gases means which do not react chemically, are kept in a closed container, the total pressure exerted by the gaseous mixture is equal to sum of the partial pressure of the individual gases. That is, total pressure P is equal to P1 plus P2 plus P3 and so on up to Pn. P1 is partial pressure of gas 1, P2 is partial pressure of gas 2, P3 is partial pressure of gas 3 and so on. Now let N1 and N2 be number of moles of two inert gases. A and B inert gases means those who do not react with each other, which is filled in a container of volume V at a temperature T. So the total pressure of the container P may be calculated as PV will be equal to N1 plus N2, N plus 1 N2 will give you total number of moles into RT. And partial pressure of individual gas is calculated at PA into V is equal to N1 plus RT. PB into V will be equal to N2 plus RT. On addition of equation 2 and 3, we get PA plus PV into V is equal to N1 plus N2 into RT. On comparison of equation 1 and 4th, we will get total pressure is equal to partial pressure of A plus partial pressure of V. That is P is equal to PA plus PB. On dividing second equation by first, we get PA divided by P equal to N1 divided by N1 plus N2. This represents mole fraction of gas A. So PA is equal to XA, that is mole fraction of gas A into total pressure. So XA is the mole fraction of gas A, P is total pressure and PA is partial pressure of gas A. Similarly, dividing third by first, we get PB is equal to XB into P. That is, partial pressure of a component gas B is equal to its mole fraction into total pressure. Applications of Dalton law of partial pressure. Mole fraction of a gas in a mixture of gases is equal to partial pressure of gas divided by total pressure of all the gases, that is mixture of gases. Percentage of gas in a mixture is equal to partial pressure of the gas divided by total pressure into 100. Pressure of dry gas which is collected over water is equal to total pressure is equal to pressure of moist gas, which is equal to pressure of dry gas plus partial pressure of vapor pressure. Now the partial pressure of water vapors is called aqueous tension. So pressure of dry gas is equal to total measured pressure minus aqueous tension, and aqueous tension is directly proportional to absolute temperature. Therefore, aqueous tension is calculated at a particular temperature at which the gas is being collected. Limitations of Dalton's law of partial pressure. The first point, it is applicable only for inert gases. Inert gases means which do not react chemically, like N2 and O2, N2 and Cl2, etc. It is not applicable for chemically reactive gases like H2 and Cl2 because they will result in the formation of HCl. Same way, carbon monoxide and chlorine, they will react to form phosgene gas COCl2. Next law we are taking is Avogadro's law. According to this law, under the same conditions of temperature and pressure, equal volume of all gases contain equal number of molecules. That is, volume is directly proportional to number of moles or number of molecules at constant temperature and pressure. V is volume and N is number of molecules. Molar volume or gram molecular volume is 22.4 liters or 22,400 ml of all gases at STP. STP means standard temperature and pressure. Temperature is 273 Kelvin, pressure is 1 atmosphere. It is the volume occupied by 1 mole and it is called molar volume or gram molecular volume. And all gases at STP occupy volume equal to 22.4 liters. The mole concept. Mole is defined as total amount of substance that contains as many basic units as there are atoms in 12 gram of isotopes of carbon 12. The mole can also be defined as Avogadro's number of particles, which is equal to 6.023 into 10 to the power 23. Loschmidt number, it is number of molecules present in the volume of gas in 1 cubic centimeter at STP. 1 cubic centimeter is also called 1 ml at STP. Its value is 2.617 into 10 to the power 19 per cc, that is per centimeter cube.